And we're off. So this is where we ended up on Wednesday. And we're going to be talking about these diagrams a lot today. So let's kind of go back over what's going on here. So we have temperature on the y-axis, time on a logarithmic axis on the x. So right here, this red line, for this time temperature transformation diagram is the transformation temperature. This is, as I told you, we're going to be dealing with the eutectoid transformation. So the gamma to alpha plus Fe3C transformation, right? So what is constant for this? So this chart, I would have to make an entire new chart if I change the composition, right? And you'll see in your text, it'll tell you in the table caption what the composition is for this diagram. The other thing I said is that this is an isothermal TTT diagram. Okay, and so the question came up in the morning, like, well, how does that work with cooling rate? Like, we think of cooling quickly, but now I've said, well, we're doing this isothermal cool. And so here's what that deals with. Yeah, down here. So let's say, for these isothermal diagrams, what I said is that the idea is we're taking a piece of metal, we're instantaneously cooling it below the transformation temperature. So somewhere below the eutectoid temperature, and then we're seeing how long this transformation of gamma to pearlite takes. And what are the two steps in that transformation? Nucleation and growth. Okay? So they're competing mechanisms. As the undercooling, as the temperature we cool it to goes down, what's easier? Nucleation is easier, but diffusion is the process by which growth happens. So diffusion is very difficult at low temperatures, and so that's going to be harder at low temperatures. So we find, in our TTT diagram, we find that nose where between at some moderate undercooling, where this combination of nucleation and growth happens such that the transformation process takes the minimal amount of time. So all through this, delta T, if we have a large delta T, that means that we are relatively far below the transformation temperature, where this transformation is taking place. That is analogous to a faster cooling rate. So you'll see kind of both things when we show videos in class, like we showed something with a steady cooling rate on Wednesday, the video we looked at. But the diagrams were dealing with this concept of undercooling because it makes the understanding of the source of the TTT diagrams, and makes using them much easier. A continuous cooling diagram, something where we have a steady cooling rate, is much more complex. I'm not going to be asking you to deal with those, but I do want you to deal with something that's a simpler version of cooling rate or cooling temperature on transformation, the TTT diagram. So if we have a small undercooling, that means we are close to the transformation temperature. So that would be analogous to a slower cooling rate. Does this make sense? Yes. The trade-off between those. Okay, so if delta T is large, delta T is the transformation temperature minus whatever temperature we're at. So delta T is kind of like an absolute value measurement of how far we moved below the solidification temperature, the transformation temperature. So what I would want you to know as far as nucleation and growth is for which of these delta T's is nucleation easier? Small delta T or large? Nucleation is easier. And here growth is easier. And why is growth easier at high temperatures? Diffusion. That's a pretty standard answer. I'll let you know if that changes at any point in this class, but if something's much easier at high temperatures, diffusion is usually going on, that or some kind of chemical reaction. And so why do we care? We're actually going to spend a lot of time today talking about different microconstituents and different phases in this iron-carbon phase diagram, because that's the source of all of the magicness of steel. Okay? Well, why do we care so much about this? Why do we care about the processes and the phase transformations that are happening at 650 or 500 degrees C? It's not because we're going to use the steels at that temperature. Okay? What's happening when we make a steel component or when we make a steel microstructure, when we process it, we're cooling it. And that cooling has a path, right? We can get it from 800 degrees C down to 25 degrees C a lot of different ways. And the path we take determines the final microstructure. Because at room temperature, diffusion is almost impossible. Okay, so we want to, all of this is, as we're looking at these microstructures, these aren't the microstructures at 500 degrees C. They're the microstructures that formed because that gamma to alpha plus cementite transformation took place at a certain temperature. And then it's formed, and then we cool it down to room temperature, and it's locked in. That microstructure is locked in. Does that make sense? So these are the microstructures that our steel components are seeing when we put them in cranes and buildings and robots and roller coasters and hope that they don't kill people. Okay. Robots can kill people. I've seen the movies. Okay. Well, just robots are cool, I mean. Okay. So we talked, let me go back here. So what we're seeing, we talked about pearlite. So this is the one we've been talking about. Why? Because it's the equilibrium eutectoid microconstituent. Equilibrium means it's what's going to form if we cool it slowly enough and maintain equilibrium as we go through. Eutectoid means it's that lamellar back and forth, and it's happening because of this eutectoid transformation. And a microconstituent is this combination of the two phases, alpha and Fe3C, and their orientation with respect to each other in the microstructure in 3 dimensions. So far we've learned about pearlite. So this is what's happening. We cool it instantaneously down to, say, 625 degrees C. Right there at time 0, right as we hit 625 degrees C, what phase do we have? We still have austenite, right? The transformation hasn't taken place. It takes time. So at T equals 0, we still have austenite. When do we start to form pearlite? Right here. You can read log charts, right? It's about 20 seconds. Halfway between is about 30. 2 seconds, yes. Sorry. Thank you. So about 2 seconds in, we start forming pearlite. Fabulous. How long before we form 100% pearlite? This line, right? Where does this temperature, this isotherm, the holding temperature, hit the 100% pearlite? Right here. So that's, 15, 20-ish in there. You can figure it out, right? This is half. So it's 10 to the 1.2, whatever that is. That's what this line up there is. Okay. So how long did the transformation take? Let's just say, for the sake of making my life easier, that it's 15 seconds. How long did the transformation take? 15 seconds, not 13. So I'm just kind of put that one in your head. That's the way we talk about it, okay? We're always taking the transformation time from t equals 0 from over here. Or since there's no 0 on a log axis, t equals 1 times 10 to the negative 1. Any questions about that? Okay, now we've talked briefly before, you guys have raised questions about, well, what impacts the thickness of those layers? Oh, so this is what happens. Somewhere in there, so we're now at a gamma plus perlite. Now that we've brought time in, where it's not a phase diagram, but in that time, temperature range there, we have both gamma and perlite. Not stable, but we have both phases, right? Which one's the stable phase? Alpha and cementite. Perlite's the stable microconstituent. But it takes time to happen. So we end up with full perlite, and it took 15 seconds. Now, we've talked before that we can change the thickness of those laths, right? We're not changing the relative amount of cementite or alpha. Okay, that should have become clear over your recitation. If you still have questions, come see me afterwards or in office hours. But we are changing the thickness between coarse perlite and fine perlite. So if we have the transformation happen at small undercooling, so delta T is small, we will form coarse perlite. It's coarse in two ways. These kind of subgrains that you see here, okay, so you can see kind of like 4 different areas there where the lamellae are pretty much going about the same way. Over here, a subgrain is that guy, that guy. There's some grain boundary alpha. Much smaller subgrains and much thinner laths. The subgrains are smaller because the nucleation is happening more quickly, right? At a larger undercooling, we're going to nucleate more of these sites, so we'll get an alpha ferrite lath start forming. And immediately, because the concentration of carbon's higher next to it, we'll get cementite laths, and then because the carbon concentration is lower next to it, so we'll form these lath structures with symbiotic growth of the two phases together, but we've nucleated more of them. So each of the subgrains is smaller, the same way that like a polycrystalline material is smaller. The grains are smaller for fast cooling rates for a polycrystalline single-phase alloy. They're thinner as well because that process of shooing or pushing carbon out of the alpha lath to keep it forming is a diffusional process, and so it's not going as far at lower intercoolings before it starts forming, right? The flux is lower. We're not getting the carbon as far away as quickly. So we have thinner laths and smaller subgrains. What do you think that will do for the mechanical properties? For which one?
For the smaller.
Okay. So this guy's yield strength is higher. Fine perlite has a higher yield strength, higher tensile strength, higher hardness than coarse perlite. But it does have a lower ductility. Because why is fine perlite stronger? We've increased its strength. What have we done? How did we do that? Okay, by the grains. But the basic idea of strengthening was, what are we doing to increase the strength of a material?
Blocking dislocation motion.
We're blocking dislocation motion. So anything we do to block dislocation motion is going to reduce ductility. Okay, so it's still just the same strengthening mechanisms as grain size refinement. It's the same thing in play there. Any questions about this? Okay. So this is a non-equilibrium transformation product. And we talked about this briefly. We didn't talk about it in great detail. But this is bainite. So let's go back and look at that perlite image. This is 10 microns. Okay? For bainite, this entire image is 5 microns. So what have we done by having a large undercooling where the T transformation is low? Say, I doesn't have it. Say about, 300 to 500 degrees C. A few hundred degrees below the transformation temperature. If we can cool it instantaneously that low, we've really inhibited diffusion. And so now the symbiotic growth of alpha and cementite lacs together is not going to happen. What's going to happen is we'll nucleate the alpha lacs, but now we'll have little rods or particles of Fe3C in the alpha lac. So let's go back. So 5 microns, this would be the size of that little needle that we saw in the image. So there that needle would be, for a bainite, we'll go back here, this guy right here, and the perlite had like a structure like that, right? With the lacs. Look instead what we have. These dark bits, that's still cementite, just like the dark pieces between the lacs, the cementite, and the perlite images. But we have tiny rods of it, or particles. So now we've changed the distribution of this hard phase within our material so that we have lots of tiny pieces close together. What do you think that does to the strength? Who says that? Okay. Why? What is that analogous to that we learned about? I hear mumbles over here. I'm really waiting for somebody in the way back to just yell out the answer, because you guys know it too. Okay. So this is basically just like precipitation strengthening or precipitation hardening. Those little bits of cementite are making it hard for dislocations to move. And we've got very little ones very closely spaced. This is good. Okay, but completely different morphology than perlite. Same 2 phases, okay? So alpha plus cementite, same 2 phases, but a different morphology, so it's a totally different microconstituent or transformation product. So, now I'm going to go into the realm of the crazy. Not really crazy, but you guys can laugh at me a little bit, because today, so, who here has ever been to the morning lecture? Okay. So you show up at the morning lecture. We have a lot more fun in that one. So they're a lot more kind of interactive. It's a lot of fun. So they were trying to get me to, they were really stuck on this. What's the difference between perlite and bainite? Like, what's going on here? So this was the analogy I kind of finally landed on. So imagine you have a giant birthday cake that's a foot tall. Okay? Have you ever seen the movie Matilda? We're going to, that giant chocolate cake in the movie, that's what we have. Okay. So let's take a slice of that cake. And in coarse perlite, we only have 3 layers. I knew you were going to laugh at me. So this is coarse perlite. They said I still had to use this analogy, even though you guys aren't as much fun, because it was helpful. So if it's not helpful, I'm trying. Okay. Now, who here has had a slice of cake from Mozart's? Okay, like the ones with 10 layers, like they take that layer of cake and they slice it really thin, and I don't know why it tastes better that way, but it does. So they have thinner layers of cake, so same shape of piece. Let's put it on a plate, because we're really fancy now, we're not just serving it on a napkin. What'd you say, Rich? That's probably it, right? Okay, not in this analogy. We have not changed the ratio of icing to cake. Let's be very clear about that. Okay, but now we have lots of little layers. This one's fine, perlite. What do you guys think of the analogy? Raise your hand if you like it. Raise your hand if it makes you hungry for cake. Okay. Bainite, totally different. We do not have a layer cake anymore with bainite. Okay? What we have is a funfetti cake. Have you ever made a funfetti cake, like you mix the sprinkles into the batter? That's kind of like what this is. So legitimately, either it helped you or it didn't, but at least it woke those of you who are sleeping up, right? And if you slept through my cake analogy, I'm cutting it out of the presentation, so ha. Maybe I won't cut it out. But I'm still angry that you slept through my cake analogy. You. Okay. So the point I want to make finally with both perlite and bainite, they're both equilibrium phases. So nothing is going to happen to the microstructure when we cool it back down. Okay? And there's still nucleation and growth phenomena. There's still a diffusional process. But something changes when we reduce the temperature, the transformation temperature is so much lower, we don't have enough diffusion to allow that equilibrium eutectoid microconstituent. We can't have that symbiotic growth. Instead, small clusters of carbon-rich areas, cementite, are forming within the alpha grains or alpha lacts. With me? Okay. There's a third one we're going to talk about today, and that's called martensite. Martensite is not an equilibrium phase. It's not on the iron-carbon phase diagram. Nowhere on that diagram is martensite because it's not an equilibrium phase. It will form if we cool it quickly enough. So say a water quench. Yes?
That dotted line is bainite.
Oh, right. Thank you. So, remember how I said the little tippy tip of the nose was important? That's the perlite bainite boundary in steel. Where that tip of the nose is, we're going to get a different morphology of the equilibrium phases. What do you think? Which one's perlite? Up here or here? Take a look at it and then we'll go over it. You can talk with your friends, see if you can figure it out. Okay. So the fun comment from one of the front rows is like, well, there's a P and a B, so I guess that's the answer. Yes, P is for perlite, B is for bainite. But what's going on here? At these higher temperatures, diffusion is easier. Why do we form bainite? Because they can't diffuse. So this is where bainite is going to form. At these larger undercoolings down here, in this range of temperatures. Because diffusion is very limited at those temperatures. So we can only get tiny clusters of cementite. We're not really able, as an alpha grain grows, it nucleates and starts to grow, it can't squeeze out all of the carbon, right? It's like it's growing, but the carbon's still kind of trapped inside that lath. And so it's just going to form little bits of cementite. It's not going to be able to move from the insides of the lath to the outside. So that's why we're forming bainite at lower temperatures. Yes?
What is happening at that boundary line?
So we generally wouldn't do a transformation right at that boundary. So it's not like, that boundary is not like a clear cut and dry, like here it's stable and there it's not. But that nose of the curve is, generally the place where that difference is. So right in here, we might get some weird sections where perlite, really, really fine perlite forms, some where bainite formed. I mean, that's kind of outside the scope of this class. Really, I just want you to understand, why would we get bainite instead of perlite when perlite is the equilibrium structure? That's the way it wants to form. That's the way it forms when we were talking about phase diagrams. We wouldn't get it if we inhibit diffusion enough. We're not going to allow that to happen because equilibrium requires slow enough cooling to allow for diffusion. So that's where that boundary is. And then we have this third microconstituent, martensite, or this third phase. Actually, it's a totally different phase. And it is not an equilibrium phase. It's not even cubic. And it's a diffusionless transformation. It involves single atom jumps. So we cool this down quickly enough, and the atoms basically say, oh, pop, now I'm going to be in a martensite phase. It does exactly what they said. It sounds just like that. If you listen really closely, you can hear them saying it. No, but so they go from a cubic gamma structure, so FCC cubic structure, and move just jump into this body-centered tetragonal phase. So there's a change in shape associated with that. We're moving to a less dense structure. Okay? We now have a not entirely close packed. So what do you think is going to happen about this? What do you think dislocations are going to be like moving through martensite? If they're not close packed. It's much harder, right? Dislocations want to move along those close packed directions and planes, because then the actual movement of a line of broken bonds, or that extra plane of atoms, if you go back and look at how we look at dislocation motion in 3 dimensions, much harder if I have to, hopping, if I have to hop from here to the other side of the stage. Much bigger energy barrier. Dislocation slip is very, very, very difficult now in this body-centered tetragonal phase. Here's the weird thing about martensite. It's diffusion-less. So the amount of martensite that forms is dependent only on the temperature. Okay, so let's say we start from up here, like 750 degrees C, and we cool it down immediately to 200 degrees. What do we have? What 2 phases do we have now? There's no alpha and no cementite. We had some austenite that we started with, and now we have somewhere between 0 and 50, we'll say 25% martensite. The rest is austenite. It's called retained austenite, that if you cool it quickly enough, you're not allowing diffusion to happen, you're not allowing the equilibrium phases to form. So this is a very classic use of bypassing equilibrium to get a certain kind of microstructure, a certain set of properties. So the amount of martensite is only dependent on the temperature. So if we left that alloy at 200 degrees, it would stay 25% martensite. And the only way we're going to get more martensite is if we cool it down more. And once we cool it to room temperature, it'll be, for all intents and purposes, 100% martensite. There is a tiny bit of retained austenite because of the shape change. Right, we're moving from a dense to a less dense pack, so in that movement there's going to be teeny tiny pockets of austenite, but martensite forms as these needle shapes. Okay? But the important thing that I want you to know about martensite is it's very hard it's diffusionless, and it's not an equilibrium phase. Any questions about what martensite is? It is not an equilibrium phase. So if it's not an equilibrium phase, let's say we take a piece of perlite, a piece of bayonitic steel, pearlitic, bayonetic, and martensitic steel at room temperature. There is no driving force for the pearlitic or bayonetic steels to change, to have any sort of phase change. There's no driving force for any of that to happen. Not so for the martensitic steel. It is not in equilibrium phases, and so there is a driving force for it to change. And if you heat it up above this temperature, it will. Yes?
If you cool it like halfway down,
We'll get into that.
make some perlite, could you cool it further, like instantaneously, and make martenite?
Yes. So his question was, let's say we cool it, make some perlite, can we then just like instantaneously cool it to room temperature and make the rest martensite? Yes. And that's what we're going to talk the rest of the lecture today about, because that right there, so you look at this, why do we care? Why am I making you learn yet another graph? 2 reasons. It's good, you need to understand kinetics. You know, these things take time, and that factors into things. The other thing is, what is steel? Yes, thank you, Richard. Steel is magic. Why? Why do we have so many different kinds of steel? One of the reasons is that we have a more complex phase diagram, right? We had a lot more equilibrium phases than, say, for a nickel-copper alloy. The other reason is that we have the ability to target this microstructure in a number of different ways to get these different micro-constituents. So not only do we have more phases, not only is there a huge difference in strength between those 2 phases, alpha iron very ductile, and cementite very hard and brittle, so we can get some really interesting strengthening mechanisms going on, but we also can change the percentage of different micro-constituents. We can have 10% perlite, 25% bainite, and the rest martensite. So let's see how that looks. Well, we're going to talk more about this later, the tempering of the martensite. But first, let's consider something relatively straightforward. Let's say I want 100% coarse perlite. What am I going to do? Where's coarse perlite going to form? Here or here? 1 or 2? Temperature 2, right? Higher temperatures, less nucleation, more faster growth. Okay, so we'll do an instantaneous cool to 675 degrees C. Okay. And then how long do we have to hold it for? About 300 seconds. Right, he said right here, so that's 10 to the 2.5. So we'll hold it for about 300 seconds. We'll get 100% coarse perlite. If I want 100% fine perlite, is that going to take more or less time? Less time, so I'm going to be closer to the nose, right? The transformation is faster the closer we are to the tip of the nose. So we're going to cool it to 575 degrees C and hold it for how long? Like 8 seconds. So about 10 seconds. We'll build a little space there. And then we can quickly cool it down to room temperature. And we will lock those microstructures in. As long as we don't heat it back up to the gamma phase, we're going to keep that microstructure or do anything weird with the environment it's used in. Okay. If I want 100% bainite, I need to go below the tip of the nose. So let's say we go to 450, and how long do I have to hold it for? About 30 seconds, right? 10 to the 1.5. If I want 100% martensite, I would have to go from above the austenite base field down to room temperature, basically, or 100 degrees C, and how much time? Less than 1 second. I have to avoid that nose. Huge, so you can see it's not like super easy to make martensite. And actually what we'll see is that if we add carbon, it'll move the nose that way. But we'll talk about that later. Okay, now let's talk about some combinations. So we're going to have this certain set of yield strengths. Let's talk about coarse perlite, fine perlite, bainite, and martensite. Which has the lowest yield strength? We already talked about coarse perlite is less than fine perlite and bainite. What do you think about martensite? Very hard. So actually, as we move this way, the sigma yield strength increases and the ductility decreases. And we know that a barrier, like a grain boundary, where we're moving from one phase or one orientation to another, can serve as a barrier to cracks and dislocations. So we can, customize our microstructure. So let's say I want 50% fine perlite, 50% bainite. What's the first step? What temperature do we want to cool it to in the first step? Okay, 575. I'll roll with that. It's the one we used before. That's good. Close to the nose, but not below it. How long do we want to hold it for? Now less than 30 seconds. We want to hold it to here, right? We want to hold it to the 50% line. So that's about 3 seconds-ish. 2 or 3 seconds. So quench it to 675 degrees C. And we'll split the difference and say hold it for 2.5 seconds. Huh? Yeah. No. So halfway between 1 and 10, we'll just say that's 3. Yeah, thank you. That would be, what kind of perlite? Coarse perlite, right? I broke my computer. I'm not sure which would be worse. Okay, so that should say 575 degrees C. And if I can figure everything out, I'll fix it. So what's the next step? Yes? Might be a little bit. What would happen if we cooled it, had the transformation at 500 versus 300? Yeah, it would be a little bit coarser, a little bit finer, but it's not as big of a difference in terms of mechanical properties as is the difference between coarse and fine perlite. So we don't necessarily, so her question was, what if we formed bainite at 500 degrees C, what if we formed it at 300 degrees? The microstructure, the fineness there would change a little bit. Certainly the mechanical properties are always going to change with heat treatment, right? And so that's the other thing, is the material, same chemistry, change if we change the cooling path? Is it still the same material? To a materials engineer, no. And should be no to you, because it's going to have completely different mechanical properties. Completely different properties. When we look at a material, if you're going to get a spec sheet for a steel, it's going to have information there about its processing history, because that is absolutely going to affect the microstructure and absolutely affect the properties. Okay. Yep, it's broken. So once we get to, we've held it at 575 degrees C for a few seconds, and we come here. Once we do that, what's our next step? We want to form bainite. We'll cool it down, right? We take another jump down in temperature. Now here's my question. What did we end up with when we went from right here, at the end of this first step, what do we have? Okay, 50% fine perlite. What's the rest? 50% austenite. Does that make sense to everybody? We have half perlite, half austenite, right? We're in the middle of that austenite to perlite transformation. So now, if we want to get 50% bainite, what's going to happen? Is anything going to happen to the perlite if we drop the temperature? Exactly, no. Nothing's going to happen to that perlite. It's an equilibrium phase, equilibrium microconstituent. There's no driving force for it to change if we cool it down. We're locking in that half part of the microstructure. What is going to change? The austenite. So it's very analogous to when we started forming, or this step is analogous to, when we would form that blob alpha or primary alpha, and nothing happened to it when we went below the eutectic temperature, right? It stayed. But all of the remaining liquid changed to alpha plus beta, right? So we had liquid plus alpha, but it was the liquid that went to alpha plus beta. So now what's going to happen is the gamma, the austenite, is going to go to bainite. So we're going to cool it down to 400 degrees C. And so, I know I still have like a minute, I have 3 minutes left, so I understand if you guys don't want to come and you want to leave early, but please try not to. Well, why am I talking to you guys, right? You're like, dude, you're preaching to the choir. So tell your fellows next time not to make such a loud noise about it. Some people actually care what I'm saying. Maybe. I like to fancy. So now, all of the austenite is going to bainite. So we cool it down to 400 degrees C. How long do we have to hold it for? To here? No, we have to go to the 100% bainite line. So we're going to hold it for 100 seconds. Yes?
Is that 100 seconds in addition to the 3 seconds?
Yes.
Okay.
And here's the thing. When we move from one temperature to the next step, time starts over. It's a totally different transformation. This first step, this was the gamma to gamma plus perlite. This next step is the gamma to bainite. All right, the same gamma now comes down here. And we have now half perlite and half bainite. So the two things you need to think of is when you move from one to the next, think about what's happening next, okay? So it's not half of the bainite transformation happening, it's the entire thing, and time resets. We're going to pick up with this on Monday, and you're going to do some of these in recitation next week, because you're going to be tested on